In this problem, we're analyzing a complex, and it's made with the exciting metal nitnium. Dun, 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 dun. Specifically, we're trying to find the charge on our central metal nitnium and the coordination number. So I always like to start on the outside of these and then work my way into the coordination sphere. So what I mean by that is each bromide has a charge of -1, which means that total the bromides are contributing -2. So the complex must be +2 to counterbalance that. Now we can work our way over to the nitnium and see what the oxidation state of our metal is. Each chloride has a charge of -1 for a total of -2. Ethylene diamine, or En you'll recall, is neutral, so it's not contributing any charge. Since our entire complex needs to add up to +2, that means nitnium must be in its +4 oxidation state here. Okay, now the coordination number. So the coordination number, I like to think of as the number of parking spots available inside the coordination sphere. So it's how many lone pairs of electrons are being donated to the central metal. So I have up here the structure of ethylene diamine. And remember, ethylene diamine is a bidentate ligand. That means it can donate 2 lone pairs of electrons to the central metal. So in this case, if we have nitnium 4+, this nitrogen can donate a lone pair of electrons, this lone pair can donate, or this nitrogen can donate a lone pair of electrons. Bidentate literally means 2 sets of teeth because it can bite onto that central metal complex with these 2 lone pairs of electrons. So considering ethylene diamine takes up 2 spots, and there is 1 of them, and that each chloride takes up 1 spot, so chloride is monodentate. So each chloride takes up 1 spot, but there are 2 of them. Our total coordination number here is 4. Again, 2 spots coming from the ethylene diamine, and a total of 2 spots coming from the 2 chlorides we have there. So choice D, FTW. In this problem, we're trying to find an equilibrium pressure. So we're given a Kp, and remember Kp is just products of reactants, but specifically it uses pressures. So pressures are directly proportional to concentrations, so we can utilize them here. And it's going to be products, so the pressure of the NOI gas over the pressure of nitric oxide squared, because of that 2 here, then times the pressure of the I2 gas. And we're given 2 of these pressures, and we just have to solve for the 3rd one. So let's do just that. So here's our setup. We have our Kp here, and we have the 2 pressures that we know here. And we're trying to solve for the pressure of NO. Alright, so first thing we'll do is multiply this through. Now we'll divide both sides by the point 0.0704. Then we'll take the square root of both sides, and we'll end up getting that x is equal to 0.43. And remember, we were solving directly for the pressure of nitric oxide here. So it is choice B. In this problem, we're given a KSP and a KF. So the first thing I would do is write out what those reactions mean. Remember, with a KSP reaction, it means that you're breaking apart something, generally speaking, a sparingly soluble salt. With a KF reaction, it means a formation constant. So you're forming something, generally speaking, a complex metal ion. So let's see what happens if we combine these two reactions together. Well, our lead will cancel out, and we'll end up with lead sulfate plus 4 chlorides yields lead chloride complex thing, to use only the most technical of terms. And sulfate. Now, I don't want to alarm you, but this looks awfully familiar. Where have we seen it before? Wait a minute! Aha! It's the equation that we're looking for the K for. Well, since we got this reaction by combining the KSP of what's being broken apart with the KF of what's being formed, we can find the KEQ. And our KEQ here is just going to equal the KSP of what was broken apart times the KF of what was being formed. When we do this, we will get our KEQ for our overall reaction is equal to 4.5 times 10 to the 7th. So by coupling this not so favorable dissociation of lead sulfate with the very favorable formation of this complex, we were able to make our lead sulfate substantially more soluble. So next time you're trying to dissolve some lead sulfate, just keep this in mind. Ooh, in this problem, Rick T. Cat needs to plate some gold claws. Cool. In any electroplating problem, I like to write myself 2 reminders. The first reminder is what a Faraday is. So, 1 Faraday. Remember, a Faraday is a mole of electrons. And the reason why that's important is we can relate our number of electrons to the amount of charge. It's 96,485. I'm just going to put 96,500 coulombs worth of charge. The other reminder that I like to remind myself is what are amperes? So here he has a current of 60 amperes. And that means that he's able to get 60 coulombs worth of charge for every 1 second. Both of these are going to be invaluable conversion factors as we go through this problem. Now we want to write our reaction. So since gold has 3 nitrates on it, that means that gold must be in its 3+ oxidation state. So our reaction is going to be Au 3+ aqueous. And to get to solid gold, that means that each gold cation is going to require 3 electrons to make Au solid. Let the dimensional analysis commence. So he wants to plate 10 grams of gold. Well, we'll need to convert this to the universal currency of chemistry, the mole. There are 197 grams of gold for every 1 mole of gold. And then how do we relate this back to electrons? Well, we can see that for every 1 mole of gold we want to make, it'll take 3 moles of electrons. So that's going to be another conversion factor here. So 1 mole of gold requires 3 moles of electrons. And then the next thing we want to do is relate this to charge. So 1 mole of electrons equals 96,500 coulombs worth of charge. Okay, that's that conversion factor that we saw before. I always like to stop at coulombs kind of as a checkpoint in the middle of the problem because it's going to be the connecting factor between this thing. So I'm just going to solve and figure out how many coulombs of charge Rick T. Cat needs here. So grams of gold will cancel out. Moles of gold will cancel out. Moles of electrons will cancel out. And we'll be left with 14,700 coulombs of charge. Okay, now we need to relate this back to time. And this is where our amperes are going to come into play, because this can relate the amount of charge, coulombs, to time, seconds. So, once again, we're going to do our dimensional analysis. So, 14,700 coulombs. For every 1 second, we get 60 coulombs worth of charge. So coulombs will cancel out, and this will end up equaling 245 seconds total. In this problem, we're going to qualitatively evaluate some ligands to figure out which ones create the largest crystal field splitting gap. You'll recall that the energy difference between the 3 low energy d orbitals in a transition metal complex and the 2 high energy orbitals actually happens to correspond with the visible spectrum. So what this means is that visible light can come in, and boom! An electron can absorb that energy and be promoted to a higher energy orbital. Whatever color is absorbed, let's say, in this case, red light, well, we don't see that color because it's getting absorbed by the complex. What we would, however, see is the complementary color. So in a problem like this, I like to add actually a third column here. And that third column is going to be, wait for it, color absorbed. Because it's the color that's absorbed that corresponds to the crystal field splitting gap. So if something appears green, that means again that it is absorbing red. If something is appearing orange, it is absorbing the complementary color, blue. The blue complex must be absorbing its complementary color, which once again is orange. And the yellow complex is actually absorbing violet. Now, let's consider the visible portion of the electromagnetic spectrum. Whoop-pow! Here we have the visible portion of the spectrum. Oh. And to analyze this, specifically the energy of the colors, I like to think about what comes beyond red and beyond violet. So if we consider the type of wavelength that you get beyond red, it is infrared, or IR. Beyond violet is, appropriately enough, ultraviolet. So if we consider, for example, the sun's rays, which one of those is higher in energy? Well, it's going to be the ultraviolet ones. So this side corresponds to a higher energy, whereas the red side corresponds to a lower energy. So in terms of wavelength, red light is longer, more undulating waves, whereas violet has shorter waves. Those look great. So now if we analyze the colors absorbed here, we can see which one is the lowest and which one is the highest. So I'm just going to rank them from lowest to highest, where 1 is the lowest and 4 is the highest, just to put them in order here. So red is the lowest energy color here. Next we have orange, then blue, and then violet is the highest energy. So our order ends up being bromide is the weakest field ligand here, then ammonia, then carbon monoxide, Then finally cyanide. So choice B ends up being the correct order. This problem deals with thermodynamics, and we can take two different approaches. First of all, we can use what we inherently qualitatively know about the process of vaporization. So vaporization, where we go from a liquid to a gas. You might already know in terms of the enthalpy and entropy what this is. We can also do a quantitative approach here and actually get some numbers. So I'm going to solve for the actual values here, but that's not necessarily necessary to do. So vaporization is the process where something goes from its liquid state to its gaseous state. So we can use the products minus reactants rule to figure out what the enthalpy and entropy changes are associated with the vaporization of tickle. So here we have our setup for the products minus reactants rule. So this ends up being positive 41 kilojoules per mole. As with any vaporization process, this is an endothermic reaction. It needs to absorb heat to do this. So if we're solving for the entropy, we can set up our products minus reactants rule. And it ends up being 133 joules per mole Kelvin. So again, vaporization will always lead to an increase in entropy. So it's always endothermic process that leads to an increase in entropy. So for this reaction, we have one aspect that's thermodynamically favorable for a reaction, an increase in entropy, and one aspect that's thermodynamically unfavorable, the fact that it's endothermic. So this is going to have a temperature-dependent spontaneity. And to figure out how that's going to be, let's consider one of our most classic equations. Delta G equals delta H standard minus T delta F standard. Now remember, standard enthalpy and entropy do not change that appreciably with temperature. Delta G, however, changes wildly. I mean, temperature is one of the factors inside of our equation. So let's consider this equation and these thermodynamic properties to figure out if this is going to be spontaneous at high temperatures or low temperatures. At a very low temperature, for example, 0.000004 Kelvin, don't want to do absolute zero here because there needs to be some movement for reaction to take place. Well, this really low temperature is not going to affect this delta H term, right? Because T is not a part of it. So this is going to be unscathed. Our delta G is going to equal some positive number. In this case, we have the value that we solved for before if we wanted to put some actual numbers with it. And this is going to be minus. Now, if this is really, really small, it's going to have a big impact on this T delta S term. So here we'll have a positive number minus a very, very, very small positive number. Okay? So, in fact, for all intents and purposes right now, this value is practically zero. Okay? So if you take a positive number minus an itty-bitty positive number, that's basically zero, what are you going to end up with? Well, at this temperature, the delta H is the determining factor here, and we would end up just having a positive value. So at low temperatures, this evaporation is going to be non-spontaneous. Now, let's consider the other extreme. High temperatures. For example, 1 billion Kelvin. Okay, so here we're going to have delta G is equal to a positive number. It's not going to be overly affected by that very large temperature, minus a positive number! A massive positive number because we have such a high temperature that it's making the T delta S term really, really, really big. Oh no, I got too excited. So, if you have a positive number minus a positive number, you're going to end up getting a negative value. Which means at high temperatures, a reaction like this would be spontaneous. So, which of these statements is true? Well, that is choice C. Now, there is another way that we theoretically could have answered this problem. Not just theoretically, you might have gone about doing it this way. Since we're looking for the process of vaporization here, well, vaporization is always something that's non-spontaneous at low temperatures and spontaneous at high temperatures. For example, water boiling, right? Under 100 degrees Celsius, it's non-spontaneous. Above 100 degrees Celsius, it's spontaneous. There's always that magic cutoff known as the boiling point. So we actually probably could have answered this in, like 5 seconds. But this process will work for any of these types of problems, not just phase changes. Another true-false question. So the first one says about a chelating ligand will form a more stable complex than a comparable monodentate ligand. So we have here an example of a chelating agent, ethylene diamine tetraacetic acid, or EDTA. And choice 1 is indeed true, because basically on this side you have 2 moles of stuff total. On this side, because the EDTA liberates the ammonia, we end up having 7 moles of stuff. That is a considerable increase in entropy. So it's part of what's called the chelating effect. One of the major tenets of it, one of the major reasons why it exists, is because of this pronounced increase of entropy that a chelate can get. Now remember, a chelating agent is any polydentate ligand. It's something that can donate more than 1 lone pair of electrons. So statement 1, ding, indeed. Statement 2, if a solution containing a metal complex is blue, yellow light is being absorbed. Well, we can consult our color wheel to figure this out, but if something is appearing blue, that means it's absorbing the complementary color, which is actually orange, not yellow. Okay, so this statement here is false. Myth busted. Okay, and for the last one, we're talking about high spin versus low spin complexes. So let's just say, theoretically, that we have 6 electrons to distribute, and let's see how these 2 different setups will affect how we distribute these electrons. So in this first situation, we have a small energy gap. Okay, so this is small. This will be created by a weak field ligand. So we can fill out our electrons. 1, 2, 3. We'll always put electrons in the bottom 3 orbitals first. And then we have a decision. Do we go up top to here, or do we pair down here? Now, because this is an eensy-weensy energy gap, very, very small energy gap that we're looking at here, it's going to be more energetically favorable to just go up top 4, 5, and then fill out the last electron down here, 6. Okay? So a weak field ligand creates what's called a high spin complex. And I like to think of it as you do 1, 2, 3, and then you go up high 4, 5 before returning to pair. Let's see how that contrasts to this larger energy gap here. Now in this case, fill out the first 3 electrons, 1, 2, 3. Now, look at how big this energy gap is. That's pretty notable to overcome. So here, the electrons are going to be more energetically favored to just pair up rather than overcoming this massive energy gap to get into these higher energy orbitals. So this is a strong field. This would be created from a strong field ligand. It's also called a low spin complex because you have to fill out all of these low energy orbitals before you work your way up to the higher energy ones. So statement 3 says a low spin complex will have a smaller crystal field splitting. No, that's not true at all. It would actually have a greater crystal field splitting parameter because it's too large of an energy gap to overcome initially when you're putting in those electrons. So that's why we're going to fill out all the low ones first before we venture into those higher energy orbitals. So 3 is false, which means that only only 1 is true. In this problem, we're looking for the greatest number of unpaired electrons given weak field and strong field ligands. So let's take a look at choice A. You'll recall this is a 3-step process. The first step is finding the oxidation state on the central metal, in this case manganese. So since H2O is a neutral ligand, that means manganese is in its 2+ oxidation state. So now let's figure out what the electron configuration of manganese 2+ is. So regular solid manganese has an argon core and then is 4s2 3d5, which means that manganese 2+, now I always recommend writing out the neutral electron configuration before writing out the cation, because it's easy to overlook which electrons are taken first. Remember, the 4s electrons are actually further out and are easier to remove than the d electrons. So for manganese 2+, we're actually going to remove those 2 electrons, and this is going to become argon and then 3d5. Okay, so we've got 5d electrons. Neat. Now we have to fill out our diagram. We're told that it's a weak field, which means that this crystal splitting parameter, delta, is not very notable. So 5 electrons, let's see where they go. 1, 2, 3, and then, we can easily overcome this measly energy gap. 4, 5. Neat. So there are 5 unpaired electrons. Well, spoiler alert, you can't get more than that for the D subshell, so A is going to end up being the answer. But let's just look at one of the wrong ones just to see why it doesn't work. Okay? So let's take a look at choice B. In choice B, we have iron, and iron is in its 3+ oxidation state here. Alright, so if we look at the periodic table, regular old solid iron has an argon core, and then it's 4s2 3d6. So iron 3+, then we're going to take these 2 electrons first, and then one of these will just be argon 3d5. So the same number of d electrons, but very different diagram setup. So now for this one we can see it's a strong field, which means it's creating this massive energy gap. So if we fill out the electrons, we go 1, 2, 3, and then, I don't know. This is a pretty big energy gap. No, actually, you know what? We do know. It's going to be more energetically favorable to just say, forget about it and pair up these electrons. So we're going to pair up those next 2, which means there's only 1 unpaired electron in this case. It's still paramagnetic, but the question's asking for the most unpaired electrons. So choice A is the winner here. In this problem, we're relating the crystal field splitting energy with the observed color. So anytime you want to relate wavelengths and energy, we can use this equation here. E is equal to hc divided by lambda. A quick important note though, here energy must be in joules per photon. Okay, so the units we're given here are kilojoules per mole. That's not going to work. We're going to need to do some converting in order to get the appropriate number. And then h is Planck's constant. So here we have our necessary constants, Planck's constant and the speed of light. Now then, let's figure out what wavelength is being absorbed here. So the first thing we're going to do is convert those 300 kilojoules per mole into joules per photon. So for every 1 kilojoule, there are 1,000 joules, and then in 1 mole, there are 6.02 times 10 to the 23rd photons. All right, so when we do this, moles will cancel out, kilojoules will cancel out, and we will get 4.98 times 10 to the negative 19th joules per photon. Now that's not a lot of energy, but remember, that's the energy in one measly particle of light. So we'd expect it to be pretty small here. Now then, let's plug it into our equation and see what wavelength this corresponds to. So we have here our equation, and we'll multiply lambda through and then divide both sides by our energy, and we will get lambda is equal to 4.0 times 10 to the negative 7th meters, and visible light is reported in nanometers. So for every 1 nanometer, there are 1 times 10 to the negative 9th meters. So we'll end up getting 400 nanometers. Cutting it pretty close, but that falls within the visible spectrum. That's going to be violet. So if it's absorbing violet, that means that it's actually appearing yellow. Okay, here we're trying to figure out which of these are going to form an acidic solution when dissolved in water. So let's just go through each one. Most of these are salts. So the first one is iron chloride, which would dissociate into iron 3 plus and chloride. I'm not going to put the stoichiometric coefficient here because it doesn't matter. We're just considering the identities of each of these. Now then, Cl minus is the what of a what, therefore making it what? If you said the conjugate base, you can't see it, but I'm doing air quotes, of a strong acid, therefore making it a negligible base, you're indeed right. So Cl minus is not going to impact the pH of a solution. But if you have anything with a positive charge that's not a group 1 metal cation or a group 2 calcium and below, it's going to be able to be acidic in a solution. So iron 3 plus, a transition metal cation, is indeed acidic. So this one, dun, 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 oops, ding. Now let's move on to the ammonium salt. Cl minus, we've seen your games before, you're negligible. NH4 plus, ammonium, well, it's positively charged, it's not a group 1 metal cation or group 2 calcium and below. So once again, this is actually going to be an acidic solution. In fact, all ammonium salts are going to have the capacity to be acidic. So indeed. All right, the next one, sodium carbonate. So sodium plus is a group 1 metal cation. So remember, those are going to be negligible in aqueous solution. Carbonate, well, carbonate has a negative charge, and it's not the conjugate of a strong acid. So therefore, carbonate's actually going to be basic. Oftentimes in these problems, just as a generalization, we're trying to see if the positively charged thing is acidic or if the negatively charged thing is a base. There are exceptions, but that's usually what we're looking at here. So this one's basic. This one is not acidic. So I'm just going to cross this out, which finally leaves us with P4O10. Okay, well, anytime you have a neutral compound that consists of one element, in this case phosphorus, and oxygen, you have an oxide. And there's a really quick and simple rule we can use for oxides. But to do it, we'll need a periodic table. Oh, there we go. So the rule is as follows for oxides. If you have metallic oxides, they are basic. Generally speaking, some transition metal oxides are amphoteric, but just for the general rule here. If you have nonmetallic oxides, well, in that case, you're going to have something that's acidic. And since phosphorus is a nonmetal, that means that phosphorus oxide is indeed going to be acidic. And then for your metalloid oxides, things along the stair step, these ones generally oftentimes tend to be amphoteric. Again, some of the transition metal ones are too. But the general rule of thumb is as you go up and to the right with your oxides, the more acidic they end up getting. So for this problem, the answers are, the ones that are acidic are 1, 2, and 4. So choice E.